morning. Today we are going to start the lecture by considering a situation where we have a device that sends out bullets. So, let me put bullets here. Which sends out bullets more or less uniformly in the forward direction, and these bullets are incident on a screen. The screen, this is the screen, which has two slits. We can call them slit 1 and slit 2. So, there is a device here which sends out bullets uniformly randomly in the forward direction, and the bullets are incident on a screen. The screen is made up of some kind of a tough material which can absorb the bullets, and the bullets are allowed to pass through only through the two slits which we have labeled 1 and 2. And the bullets which pass through are finally incident on another screen over here. So, we have a screen here, and on this screen you have some kind of a detector which can be moved up and down, which measures the bullets, which gives you a count whenever a bullet arrives here. Now, this device sends out bullets, and bullets are always sent out one by one, and the bullets go through the two slits and they finally arrive on the screen over here. We have the detector which can record, which gives you a record whenever a bullet comes and strikes it. So, and you can move this around to different places and count the number of bullets which arrive at any given point. So, let us now consider a situation where I first shut slit 2 and open only slit 1. In this situation, so slit 2 is shut and only slit 1 is open. I can now move the detector to different points on this screen, and I can count how many bullets come and hit that particular point in a given time interval. The count is always going to be, the bullet count is always going to be an integer. We never are going to receive half a bullet. So, we are not considering the possibility where a bullet somehow breaks into two and then arrives at two different points on the screen. We are not going to consider such a situation. So, the situation which we are considering, the bullet either goes through the slit and arrives on the screen, or it does not go through the slit and it gets embedded in the material which surrounds the slit. So, you are always going to receive either 1 bullet or 0 at the detector. So, if you place the detector, let us say here, and for a time period, over a time period, if you count the number of bullets that arrive here, and if you count the total number of bullets that were emitted, then you can take the ratio of these two and calculate the probability that a bullet will arrive here through slit 1, and this we are going to call P1. And if you move the detector to different positions on this screen and record the counts at different points, you can by this process determine the probability of the bullet arriving at any particular point on the screen through slit 1. That is in the situation when only slit 1 is open. And let us draw how we expect the probability distribution to look like. So, when only slit 1 is open, we expect most of the bullets to go through, and you expect to receive the maximum number of bullets at a point just behind screen 1, the slit 1. There may be some bullets which go through this slit at an angle, and there will be a spread in the bullets around this point just behind slit 1. So, the probability of receiving a bullet on the screen, or the probability of a bullet arriving at any point on the screen through slit 1 is going to have a maxima just behind slit 1, and then it is going to have a spread, and it is going to look something like this. And we are going to call this P1. So, let me remind you again what P1 is. P1 is the probability that the bullet arrives at any point on this screen through slit 1, and this is expected to have a maxima somewhere just behind the slit, just behind slit 1, and there is going to be a spread because the bullets may not be exactly in this direction, the bullets may be in the other directions also, and because of this there will be a spread in the bullets on the screen, and the probability is expected to have something which looks a pattern which looks like this. Now, let us consider the situation where we shut slit 1 and open slit 2 and repeat the same experiment. When slit 1 is shut and slit 2 is opened, we expect the probability of a bullet arriving on the screen to be maximum somewhere just behind slit 2, somewhere over here, and again there may be bullets at different angles, there may be a spread in the angles in the bullets that arrive over here from this device that emits the bullets. So, there is expected to be a spread in the arrival of the bullets on the screen also, and there is going to be a spread in the probability around this point, and it is going to look exactly like this, but the whole pattern has shifted so that the maxima is aligned just behind the slit 2. So, let me draw what we expect when only slit 2 is open. We expect something like this. When only slit 2 is open. Now, let us ask the question, suppose we open both slits and send in the bullets from this device that is emitting bullets, and then repeat the whole experiment. We move the detector to different points on this screen, and we count the number of bullets that arrive. The bullet count is always discrete. So, bullet count is going to be discrete. It is going to be an integer 1, 2, 3. So, when I put the detector at any particular position, let us say here, and record the number of the arrival of bullets. So, what will happen typically is that for some time no bullets will come, and then suddenly a bullet will come, again after some time another bullet will come, and again after some time another bullet will come. So, over a time interval there will be a discrete number of bullets that come, maybe 4, 5, 6, it will be some integer. So, we will always get an integer number of bullets that arrive at the detector. Now, I have to divide this by the number of bullets that were sent out over that same time interval, the total number of bullets that were sent out from here over the same time interval. So, for a time over a time interval, I count the number of bullets received over here, and I count and I also know the total number of bullets that were sent out at in the same time interval. So, if I divide the two, I will get the probability that the bullet reaches this point through either slit 1 or slit 2 when both slits are open. Now, and the count is going to be integers, but the probability is not going to be an integer. The probability probability P1 or P2, or when I open both of them I am going to call the probability P12. These are both all in the range greater than equal to 0 and less than equal to 1. So, they are going to be positive numbers in the range between 0 and 1, and they are going to be, they are not going to be integers, they will be some fraction in the range 0 to 1. Now, the question is, how is the probability of a bullet arriving here when I open both the slits related to the probability when the slits, the individual slits are open? Now, a bullet at any point on this screen, a bullet can arrive at any point on the screen either through slit 1. So, there may be a bullet which goes through this slit and then comes to this point, or a bullet may arrive at this point on the screen through slit 2. So, if I record a bullet over here, it could have arrived either through slit 1 or through slit 2, and the total probability of finding a bullet at any point on the screen is the sum of the probabilities that it arrived either through slit 1 or through slit 2, right. So, when both slits are open, a bullet reaches the screen either through slit 1 or through slit 2, and these are mutually exclusive events. If the bullet goes to the screen through slit 1, then it definitely does not go through slit 2, and if the bullet goes to slit the screen through slit 2, definitely to the same point on the screen through slit 2, we can be sure that it has not gone through slit 1. So, in case we have events which are mutually exclusive like this, and the event which final event which we are interested in could have occurred by through any of these two possibilities, then we have to add up the probabilities and it will give me the final probability. So, I have to add up that the probability that the bullet, so if I want the probability that the bullet arrives at a particular point, any particular point, when both the slits are open, I can add up the probability that it arrived through slit 1 to the probability that it arrived by slit 2, and that will give me the total probability. So, it is going to look something like this. It is going to be the sum of these two probabilities, and it is going to look something like this. So, at these points, P2 is much larger than P1, P1 nearly vanishes over here. So, it is going to be exactly follow P2. At same over here, it is going to exactly follow P1, because P2 is very small. The probability of it coming here through P2, the second slit, is quite small. Over here, there is a significant probability that it comes through this or this. So, I have to add up both the contributions, and there it is going to be larger than the individual probabilities, and there will be a dip somewhere in the middle, and it is going to be the sum of these two. So, what we can say is that, and this we are going to call P12, the probability of the bullet hitting a particular point in the screen when both the slits are open. This is going to be P1 plus P2. So, let me recapitulate here what we expect when we do this experiment with bullets. When we do an experiment where we send out bullets more or less uniformly in the forward direction, in all directions in this over this range of angle in the forward directions, and we ask the question, what is the probability that it reaches a particular point, what is the probability that the bullet reaches a particular point, we can close one slit and calculate the probability, that will give me P1. We can close the second slit and calculate the probability, it will give me P2. Now, if you ask the question what is the probability that a bullet reaches a particular point on the screen when both are open, it is going to be P1 plus P2, that is the probability when both the slits are open. The other very important point which I should again reiterate is that the bullets are going to arrive at the detector on the screen one by one. So, you are always going to get either one bullet coming or no bullet coming. So, if you put a detector, the detector is going to get the counts in the detector are going to occur in units of 1. You are going to either detect one bullet coming or no bullet at all. So, the arrival of the bullets is an integer event, it is integer process, and the counts are the bullet count is an integer, and which goes up in units of 1. It goes up in units of 1 every time you detect a single bullet. You are not going to detect half a bullet, right. So, the probability could be a fraction. So, you have to do the experiment over a reasonably large period of time, and you will find that the ratio of the two, that is the number of bullets that arrive at the point and the total number that is being sent out, is going to slowly approach the probability P12 that you calculate through this. So, this is as far as bullets are concerned. Now, let us consider another possible hypothetical experiment. So, this was more of a thought experiment than a real experiment. Let us consider another such hypothetical experiment which we have also been discussed, which can easily be done in reality. So, now instead of a bullet source, we have a light source. So, there is a source here with the, let us say, with any wave, need not be light. So, there is a source here which emits a wave in the forward direction. This could be a electromagnetic wave, as we have been discussing in over a large number of lectures. Electromagnetic radiation is a wave, the electromagnetic wave. So, it could be an electromagnetic wave that is being emitted by this source over here in the forward direction. It could be a sound wave or some other kind of wave, and this is incident on two slits which are located at some distance away from the source. So, there are two slits over here, and then we have a screen located far away over here. Now, the first point, unlike the bullet source, you can vary the intensity of the wave that comes out continuously, and the intensity of the wave is proportional to the amplitude of the wave that is produced out here, and it is proportional to the square of the amplitude of the wave that is produced over here. So, you can, if you increase the amplitude continuously, you can also increase the intensity continuously, unlike the bullets, which you can just increase in units of 1. You cannot increase the bullet rate arbitrarily. You have to increase the number of bullets that are being shot out by in discrete units. Now, let us again repeat the same exercise. We have two slits over here on which the wave is incident, and let us ask the question, suppose I close slit 2 and open only slit 1, what is the pattern, intensity pattern that I expect to see on the screen over here? So, I have a detector again which can measure the intensity. I move it to different points on the screen and I measure the intensity of the wave when it arrives here. So, it could be light. If it is light electromagnetic wave radiation, then I will be measuring the intensity of the light using this detector. Now, when we close slit 2 and open only slit 1, we will get some intensity pattern. We have studied this in some detail earlier on. We expect the diffraction pattern of a single slit. So, we expect the single slit diffraction pattern on the screen over here. The intensity pattern over here is going to be the diffraction pattern due to a single slit. So, it is going to have a maxima, which we know the diffraction pattern of a single slit has a maxima just behind the slit, and then the intensity falls off. There is a spread in the intensity, it does not go to 0 immediately at the edges of the slit, it has a just behind the slit. If you move away from the point just behind the slit, it is going to have a dispersion, it is going to have a spread. The spread is of the order of lambda by d, where lambda is the wavelength of the wave and d is the size of the slit that you are using. So, there is going to be a dispersion, a spread in the intensity around the point which is just behind the slit. So, when I have opened only slit 1 and if I measure the intensity pattern on the screen, we are going to get something which looks like this. It is going to have a spread, and there will be some secondary maximas which are going to be much fainter. I am not drawing them, right. We have discussed that it is going to be a sinc square function. The sinc square function, we know the secondary maximas, the other higher order maximas have very low intensity. So, I am not drawing them. So, this is just the primary maxima, it will have a spread around the point which is just behind the screen. So, it is going to look like this. Now, we are going to call this I1, the intensity when only slit 1 is open. Now, suppose I close slit 1 and open slit 2 and repeat the same exercise. So, if I measure the intensity on the screen over here, the question is, what do we expect the intensity pattern to look like? The intensity pattern is essentially going to be exactly the same as when slit 1 is open, but the whole thing is going to be shifted down, so that the center where the intensity is maximum is just behind slit 2 now. So, when slit 2 is open and slit 1 is closed, the intensity pattern is going to look something like this. It is going to be peaked somewhere here and it is going to look exactly the same. So, it is going to be something like this and this is going to be I2. Now, we also know that when we have two slits like this and we have a single wave incident on this, this produces two secondary waves, and if I open both the slits, the intensity pattern over here is not going to be the sum of the individual intensities, it is going to be the intensity. This is the Young's double slit experiment, it is going to produce an interference pattern and the interference pattern is going to have a period which is lambda by this d, the distance between the two slits. So, it is going to vary much faster than the individual diffraction pattern and it is going to be modulated by the individual diffraction pattern. So, it is going to look, finally it is going to look like this. The maxima is going to occur at the point in the middle of the two slits and is going to be modulated by this. So, I can also draw that this is what the intensity is going to look like. And the intensity pattern is going to look something like this. And we have analyzed this in great detail. So, the resultant intensity, let me write it down over here, the resultant intensity I is I1 plus I2, where I1 is the intensity of when only slit 1 is open, I2 is the intensity when only slit 2 is open, plus 2 root I1 I2 cos delta. Where, so this is a formula which we have derived, we have spent quite a bit of time discussing this. Let me just remind you what this delta is. Delta is the phase difference between the two waves that arrive at the screen from the two slits. So, delta is the phase difference. So, if I am calculating the intensity at any point, particular point in the screen, the contribution from slit 1 and the contribution from slit 2 are going to be at two different phases, and delta is that phase. So, let me write this down quantitatively. So, this is, and this term, it is this term with cos delta with the phase difference that gives rise to the interference pattern. You see, the big difference over here is that the intensity, when I open both the screens, at certain points the intensity becomes more than what I had if I were to add up I1 and I2, but at certain points it becomes less than what I would get if I were to add up I1 and I2, and it is this cosine term over here which gives rise to this pattern. So, at the points where the intensity falls below the sum, the two waves which arrive from the two slits are going to be out of phase. So, remember that the intensity, it is the amplitude of the wave which is crucial. So, the wave which is arriving at the screen, if I represent it as A, the amplitude of that wave as A in the complex notation, then it is going to be A1 plus A2. So, A is the amplitude of the wave arriving at any particular point on the screen, A1 is the part that arrives from slit 1, A2 is the part that arrives from slit 2. If I close this, only there would be only A1, if I were to close this there would be only A2. When I open both of them, there is going to be A1 plus A2. The waves arriving through the two slits are going to add up, and I am going to get the resultant amplitude A. Now, the intensity is the square of this, the modulus of this, and this is A1 plus A2, the modulus of this squared. So, this is what gives rise to this expression, where delta is the phase difference between the two waves that arrive at that point. So, delta is the phase difference between A1 and A2, and it is this phase difference between the two waves that arrive through the two slits that causes the interference, that may cause the cancellation of the waves, the reduction in the intensity at some points on the screen. So, this again is something which is quite familiar to you. The difference with the situation where we have bullets is quite clear, quite obvious, and here the intensity can vary gradually. There is, it is unlike the bullets, it does not have to increase in integer values. The intensity can be made to vary gradually by changing the amplitude of the wave. So, we have discussed the very similar situation when I use bullets and when I have, for example, electromagnetic waves. Now, let us ask the question, what would happen if I had exactly the same thing? I had a source and I have two slits which I call slit 1 and slit 2. So, this source now sends out electrons. So, there is a source which sends out electrons in the forward direction, and these electrons are incident on two slits which I call slit 1 and slit 2. The electrons which hit the region outside the slits, they are absorbed over here. The electrons which fall on the slit are allowed to pass through and then far away on a screen, fall on a screen far away, and then we have a detector which can be moved up and down the screen. The detector can detect individual electrons. So, whenever there is an electron which comes and hits the detector, so suppose I place the detector here, if an electron comes and hits the detector, it will give me a count. For example, whenever an electron hits a TV screen, it gives some light is emitted, right. So, we can have detectors which can count the number of electrons that are incident on it, and so electrons are emitted here one by one, integer. So, these are integer events, and the electrons will be incident on the screen. So, if I put a detector here and keep it on for a certain time, it is going to tell me the number of counts, the number, it will tell me the electron count. So, the number of electrons that arrived here in that particular interval of time. If I know the total number of bullets that were emitted, I can then calculate the probability of finding the bullet at any point on the screen when these slits are open. Now, let us again deal with this in two steps, in steps. So, the first situation that we are going to consider, we close slit 2, open slit 1, and we record the probability of the electron arriving at different points on the screen. Now, if you do this experiment, we will find that the electrons mainly arrive on the screen at the point just behind the slit, but then there will be a spread around it. It will not be restricted to just this point, and if you determine the probability of finding the electron at different points on the screen by moving the detector to different positions, counting the number of electrons that arrive in a given time interval, you will find that the probability looks something like this. So, it will have a spread around this value and it will look something like this. So, that is the probability of an electron coming to that a particular point on the screen when slit 2 is closed and only slit 1 is open. We are going to call this P1. Now, if you repeat the same thing, but close slit 1 instead of slit 2, then the whole pattern is going to shift, so that the maxima now occurs behind slit 2. So, it is going to, the maxima is now going to shift to this position, but the curve is going to look exactly the same and it will look something like this. And we are going to call this P2. So, let me remind you again, we are sending out electrons from this electron source. Electrons are sent out as discrete particles. The electrons can go through the slits or they can get absorbed in the region outside the slits. The electrons that go through the slits are now then incident on a screen far away, and we have a detector which we can move to different points on the screen. The detector counts the number of electrons that arrive there. So, if the detector is kept at any point for a particular amount of time and you measure the number of electrons, so you measure the electron count. This will always be an integer. You will not get half an electron coming somewhere. You will always record either one electron or no electrons at all. So, if you put a detector here and keep on sending out electrons from this, for some time you may not get anything and suddenly you may get a click, and then again after some time you get another click, and again after some time you get another click. So, you have 3, the electron count is 3 at that point. You divide this by the total number of electrons that were sent out, and if slit 2 is closed, the ratio 3 divided by the total number of bullets that were sent out in the same time will give you the probability of the bullet arriving at that point in the screen. The point here is that the electron count is always going to be integer. The probability P1 or the probability P2 or probability as such, any probability is always in the range 0 to 1. The integer, the count is always going to be an integer. The probability is going to be typically a fraction in the range 0 to 1, but the electron count is going to be an integer. Now the question is, what will happen when both the slits are opened simultaneously, and then we repeat the experiment. So let me repeat again. We now have this device which sends out electrons in the forward direction, and the electrons are incident on two slits. The electrons which are incident on the slit will pass through, the electrons which encounter the obstruction are absorbed. The electrons that pass through, we record their arrival on the screen over here. So, we put a detector here and we can count how many electrons arrive at this point. We put a detector here and we can count the number of electrons that arrive over here, etc. So, if you believe if like the bullets, if you believe that the electrons, so if you believe that the electrons reach the screen either through slit 1 or through slit 2. So, if you believe that if I measure an electron, detect an electron here, it should have come either through this or through this, then I can say that the total probability of the bullet arriving here is the probability of the bullet arriving through slit 1 plus the probability that it arrived through slit 2. So, if this assumption is correct, what we expect is that the total probability when I open both the slits, the probability of the bullet arriving here should, let me plot it here, should look something like this, very similar to what we expect if we did the experiment with bullets, right. So, the probability over here is going to be somewhere above the individual probabilities, over here it is going to be more or less equal to the individual probabilities, and this is what you expect. Now, if you actually do the experiment where you send electrons from this side on two slits like this, what you get does not look like the sum of P1 plus P2, it does not look like this, the sum of P1 plus P2, it looks like this. And this is what the probability of finding a bullet at any point on the screen when both slits are open looks like. So, there are points, notice, where the probability actually goes below the probability when only one slit was open. So, there are points where the probability of a bullet reaching the screen when both slits are open is less than the probability when only slit 1 is open, and the sum of this with the probability when only slit 2 is open. And then there are points where the probability P12 when both slits are open is more than the sum of only P1 and P2. So, this hypothesis does not work in the case of electrons. You cannot really say that the electron went either through slit 1 or through slit 2, and you cannot add the probabilities of the bullet going through slit 1 with the probability of the bullet going through slit 2 and get the probability when both slits are open. You have to change the picture of how the electron behaves when it encounters two slits like this. And the crucial point is that there are points where the probability, notice there are points, for example, this point over here, where the probability of the electron arriving here, you see, is smaller than the probabilities when the sum of the probabilities when the individual slits were open. So, there could be a situation where if I go and sit at a point, I open only slit 1, I put a detector for some time and I get 2 counts. Same point, I close slit 1 and open slit 2 and I put my detector and I get 1 count. There is a probability that the bullet can come here through slit 1 or through slit 2. Now, when I open both of them and I sit quietly with my detector there for some time, I find that I get no count at all. So, when only slit 1 is open, there is a probability that the bullet can reach here. When only slit 2 is open, there is a probability that the bullet can reach here, but when I open both of them together, I find that there is no probability that the bullet can reach here. There are situations like this which occur when I open both the slits and I send electrons in from this side. The question is, how do we explain this? Now, this is, you must have realized by now that this is very similar to what happens when we have a wave incident on the slit, on 2 slits. When we have a wave incident on 2 slits, there are points. So, when I have a wave, not electrons, when I have a wave over here, there are points where the 2 waves that come from the 2 slits are out of phase and they exactly cancel out and the intensity goes to 0. Whereas, if I had only this open, there would be a finite intensity at that point. Similarly, if only this were open, there would also be a finite intensity at that point, but when I open both, the 2 waves which are exactly out of phase cancel out and the intensity goes to 0. So, the situation that you see for the electrons is very similar to that. So, there must be something going on which is very close to what happens in waves, where you have a cancellation of 2 waves, interference. Now, let us just ask the question, under what condition do 2 waves exactly cancel out at a point? Now, 2 waves, we know that if the 2 waves which we are superposing at that point are pi out of phase, it is only then that they cancel out. Now, if 2 waves are pi out of phase and if one of them is positive, then the other one has to be negative for the cancellation to occur. Now, here for the electron, we are measuring the electron count, we are dealing with probabilities. Probabilities we know are restricted in the range 0 and 1. So, there is no way there can be such a cancellation for the probabilities. The probability is restricted in the range 0 and 1. So, when I open this, I have the probability over here. When I open this, I have the probability at the same point. When I open both, how do we explain the fact that when I open both, the probability actually goes down instead of going up? This, you cannot explain this with probabilities alone, because the probabilities we know have to necessarily be positive in the range 0 to 1. So, you cannot explain this fact that the probability goes down by using just probabilities. So, it is necessary to introduce another quantity. So, the way we can explain this is by introducing a wave associated with every particle, which is what we had been discussing yesterday, the de Broglie hypothesis. So, if you associate a wave psi with every particle, this wave is called the probability amplitude, or it also referred to as the wave function. And the probability amplitude is defined in such a way so that the square of this, the modulus square of this gives the probability. Psi itself is necessarily complex. But its modulus squared is positive, guaranteed to be in the range 0, more greater than 0, and we can always choose an overall constant to make it in the range 0 to 1. So, this we will associate with the, if we associate this positive number with the probability, then you have an explanation for this phenomena that you see over here. So, let me go through this. So, let me go through the picture through this. So, consider an electron which is sent out from this device which sends out electrons. Consider an electron. Now, associated, let us not, instead of thinking of this electron as a particle, we will think of it as a wave psi. Now, when this wave when a wave is incident on two slits, we have already discussed this. When the wave is incident on two slits, the part of the wave which is on the slits will pass through, and this will act as secondary sources. So, if you wish to calculate the value of psi on any point on this screen, so we want to calculate the value of this wave associated with the electron on any point on this screen. So, let us choose a point on the screen. We want to calculate psi here. The psi at this point is going to be the superposition of a contribution from this slit, which we will call psi 1, and a contribution from this slit, which we will call psi 2. So, on the screen at any point, psi is going to be psi 1 plus psi 2. Let me remind you that with the electron we have associated a wave. So, we are no longer thinking of the electron as a particle moving, going to the slit and going through. We are associating a wave, just like we had discussed in yesterday's lecture. So, today also we are doing the same thing. We are continuing on the same topic. With the particle we are associating a wave, and we are abandoning for the time being the particle picture. We are thinking of as the wave propagating it, and we are interested in the value of the wave on the screen over here. To calculate the value of the wave on the screen over here, you have to, the wave is incident on two slits which will act like secondary sources. So, you have to add up the contribution from this secondary source and this secondary source, which is what I have written over here. Now, if you ask the question, what is the probability of finding that electron on any point on the screen, this psi is called the probability amplitude. It is a complex number, it is a complex function defined at all points on the screen, the square of which gives the probability. The modulus square of this is what gives the probability. So, if I wish to calculate the probability of finding the electron on any point, at any point on the screen, say at a point on the screen, this point on the screen, I should take the value of psi at this point and square it. This will give me the probability of finding the electron at that point on the screen. So, I should evaluate the value of psi at that point, and this will have two contributions. You see, psi is a sum of two different parts, two different contributions, and there could be a phase difference between these two contributions, and as a consequence of this, if there is these two contributions from the two different slits are exactly out of phase, they are going to cancel out, and the resultant is going to be less than the individual psi's, psi 1 or psi 2, and you will have a cancellation, you will have a dip in the probability. So, this is going to give me the probability of finding the particle on the at any point on the screen. when both the slits are open. Now, you must have realized by now that this psi which we have introduced, the probability amplitude, is very similar to the amplitude for the wave which we have been dealing with earlier. It is exactly analogous to the, it has been introduced in a fashion which is exactly, it is so that it is exactly analogous to the amplitude of the wave which we had encountered for, say, the amplitude of the electromagnetic wave. You should think of it as being exactly analogous as far as this purpose is concerned. So, the quantity that you measure is the intensity for the electromagnetic wave. Here the quantity that you measure is the probability, and so the intensity and the probability are again related in the same way as how the amplitude of the wave and the amplitude of this probability amplitude are related. So, when you want to calculate the probability of finding the particle at any point on the screen, of finding the electron at any point on the screen, it will be the square of this. When both slits are open, it is going to be the square of this, and you can now very easily guess that this P12 is going to be equal to P1 squared plus P2 squared plus 2 root P1 P2 cos delta, where delta is the phase difference in these, between these two waves, these two probability amplitude waves that come from these two slits. So, with this, if you make, so what I have shown you here is that if you make this assumption that associated with the particle there is a wave psi, which I am referring to as the probability amplitude. Why probability amplitude? We know that the square of the amplitude gives the intensity, which is a positive number which you measure. So, the probability amplitude has been defined in such a way, so that just like you calculate intensity, you calculate the intensity for this, take the modulus, take the square, and it gives you the probability of finding the particle, which is supposed to be positive. And it is supposed to be in the range 0 to 1, which you can adjust easily by just multiplying it by a real number. And this psi is complex. So, this observed probability pattern that you get when you do when you send electrons onto two slits can be explained if you make the hypothesis that associated with the electron there is a wave. The wave is the probability amplitude wave, or also called the wave function. The square of that gives the probability. If you make this assumption, if you that there, with every electron there is such a wave associated, then you can explain the kind of probability pattern that you will get on the screen over here. Now, remember that the probability is going to be a number between 0 and 1. So, with the electron I have a wave, the wave is going to be defined everywhere, it is going to give me a probability everywhere, but the moment I measure, the moment I make a measurement, I am going to get the electron only at one position. So, although the wave is defined everywhere, the wave associated with the electron is defined everywhere, it passes through two slits simultaneously, it comes here, there is an interference, we are dealing with a single electron, there is a wave associated with a single electron. When that wave comes to the two slits, it passes through both of them, these two waves come onto the screen, they produce an interference pattern. The interference pattern, the square of that gives the probability of finding the electron somewhere on the screen. When you actually put a detector and measure where the electron is, you will find that you have one electron at a particular position. Now, if you repeat this experiment many times, you will get a count, you will get counts at different points, and then you can convert these counts to probabilities, and you will find that the probability follows this pattern. So, let me end today's lecture over here. We have really moved on to something quite new. So, I am going to repeat it again in the next lecture and in forthcoming lectures. So, let me end today's lecture over here and we shall take it up again in the forthcoming lectures.